The first problem we are going to do is problem 9.1, which states that we have a circular loop with a 20 centimeter radius, and it lies in the z-plane equals 0, which says that our magnetic B field is in the xy plane. Now we're given the B field as 10 cosine 377 T AZ milliwebers per meter squared. The first thing we should do is convert 20 centimeters to meters, and we should know that the surface area of a circle is just pi r squared. Now we can go ahead and solve this. We are going, since this is chapter 9, we're going to be using Faraday's law, which states that the V induced voltage EMF equals the negative derivative of the flux with respect to time, and this further can be simplified as the negative integral of the B over T times ds, which is just negative derivative of the B field with respect to time times the surface. So first, our surface is just pi times 0.2 squared, and our B is 10 cosine 377 T. So what we're gonna do is take the VEMF, so the negative derivative of the B. So what we are going to do here, it's going to be a chain rule. So we're going to do the outside multiplied by what's inside the parentheses. So the derivative of the cosine is negative sign, and since we already have a negative, it just becomes a positive 10 sine 377t times, now we take the derivative of 377t, it's just 377 times pi r, which is 0.2 squared. And then don't forget about the milliwebers, which is just 10 to the negative 3. And when we multiply all this out, we get a final answer of 0.4738 sine of 377 T volts. That is our final answer. So we're going to work on problem 9.2. The diagram we are given is a rectangle with a 30 ohm and a 20 ohm resistor, and we are to find IT, and it says that the B field is out of the page in the AZ direction, and it says that the area is 2 centimeters squared, and we have to find IT. So what we should do is turn this area into a unit that we can work with. So converting it into meters, you get 2 to the 10 negative 4, and our B field is given as 4 cosine 20t webers per meter squared. Given all this, which formula are we going to use? Of course, Faraday's law. VEMF equals the negative derivative of the flux over time, which will just reduce down to the negative derivative of the B field with respect to time times the surface. And we know we are looking for IT, so this is just Ohm's law. So once we find VEMF, we divide it by the resistance, and we get our IT. So we are going to go ahead and do that. So we have an IT VEMF over R. So first we're going to take the derivative of the B field. So we're going to do the derivative of the cosine, and then we'll do the derivative of inside the parentheses. So since it's a negative, the derivative of cosine is negative sign, so it becomes a positive 4 sine 20t. Now we take the derivative of 20t, which is 20. We multiply that by the surface area, which is just 2 10 to the negative 4. And we can go ahead and divide all that by the total resistance. Multiplying this out, we just get 160 over 50 sine of 20t times 10 to the negative 4. And further reducing this, we get an IT of 0.32 sine of 20t milliamps. Our next problem, 9.3. We are given a loop and that it has a radius of 0.2 meters, and it also has a resistance of 4 ohms. So it is a conducting loop, and it lies in the XY plane. The loop has a radius of 0.2 meters and a resistance of 4 ohms, and we are given the B field to be 40 sine 10 to the 4 t AZ. And then we are given in milliwebers per meter squared. So the first thing we got to do is realize that our flux is just B times S, which is just our, for this circle, it'll just be pi r squared again. So it will be pi 0.2 squared times 40 sine 10 to the 4 t. Now we are going to use Faraday's law, VEMF, which is just negative derivative of the flux with respect to time. Doing so, we are going to take the derivative of sine, which is just cosine, so the negative sticks around, so it will be 40 cosine 10 to the 4t. Then we take the derivative of inside the parentheses. 10 to the 4t is just 10 to the 4. We multiply that by pi r squared. And what we get is negative 16 pi cosine 10 to the 4t. And here we are looking for the current. So again, the current is V over R, Ohm's law, which will just be the negative 16 pi cosine 10 to the 4 t over the resistance 4 ohms. And we get a final answer of 12.57 cosine 10 to the 4 t amps. That's our final answer. So in this next problem, it says inside the 1 meter times 1 meter square shaped wire loop, there is a time varying magnetic field equal to B equals 2 sine 10t AY Weber per meter squared. Calculate the electromagnetic force VEMF induced in the wire. So here is what we are given. This is direction of the current. So it's 1 meter by 1 meter. We are given the B as 2 sine 10t in the y direction, and it is going into the page with an X. So the first thing we need to do is calculate the VEMF, which is just the electric field times dl, which is the negative derivative with respect to time of the surface of the B field times ds, which further simplifies to 2 sine 10t dx dy. So what we are going to do is equal that to the negative derivative of 2 sine 10t. The dx dy is just the area. So we take the negative derivative, 2 sine, which is still a negative, so it will be 2 cosine 10t times the derivative of 10t with the chain rule is another 10. And since the area is just 1 times 1, which is 1, just 1, so we get total induced voltage of negative 20 cosine 10t volts. Now it says show the correct polarity of the induced voltage in the figure. Since it is a negative cosine, let's go back, use a different color so that you can see. As you can see, since it is going this way and we got an answer of negative 20 cosine, we know that it will hit a negative first and then a positive. So that is the correct way of labeling that. Our next part says to calculate the current I through the resistor. So we know from Ohm's law I is just V over R, but because we hit the negative first, we put a negative there. So we take negative 20 cosine 10t over 20 ohm resistor, which we get a final answer of cosine 10t amps. And then the final part says calculate the power dissipated by the resistor, that is 20 ohms. We know power is just V times I. So we know for our answer it'll just be 20 cosine squared 10t watts. So this is another problem that says calculate the electromotive force VEMF induced in the rectangular wire loop given below. And the first instance to solve for, it says when the rod is stationary. So that means that U equals 0 at Y0 equals 2 meters, and the B field is sine 3t AZ Webers per meter squared. So first we solve for this when the rod is stationary. So how we are going to go about this is, we know that the flux equals to the integral surface of the B times ds, which is just 2 sine 3t Webers per meter. We know Faraday's law will come in handy, the negative derivative of the flux with respect to time. So we take the derivative of 2 sine 3t, which is going to be just cosine, so the negative sticks around, will be 2 cosine 3t times the derivative of 3t, which is 3. So then we just get total induced EMF of negative 6 cosine 3t volts. So now for the second instance, it says when the rod is moving to the right with U equals, so the U is 4AY. So it's going to be moving onto the Y axis, and given the B field as 2AZ Webers per meter squared. Again here, the flux, the B times ds. So here's what we're going to be looking at. We see this number that's on the x from 0 to 1 meters, and we know that this distance is 2 meters because we're given U bar as 4AY and the B is 2AZ. So let's go back and we're gonna set up the two integrals. So the first one will be from 0 to 4t of 2 dy, then the outer from 0 to 1, since that's the height of the x-axis with respect to dx. In doing so, the first one will just be 2t from 0 to 4t. So where there's a t, you plug in a 4t, which would just equal to 8t, and the 0 would just be a 0. And then we take it with respect to x, which would just be x, and you plug in an x, and that's just the 1. So we leave that. So it's just 8t. Then we go ahead and do the VEMF of the negative derivative of the flux with respect to time. The negative derivative of what we just got up here, it's just going to be 8. So our final answer is just negative 8 volts. So part C says when the rod is moving to the right with u bar equals to 4ay, and our b is given as 2y az. And we are assuming that the sliding rod starts at the origin when t equals 0. So we're going to go ahead, start with the flux. B times ds. And we are going to take the double integral of the B field, 2y. So first we're going to do it with respect to y. And integration for that is again 0 to 4t, because it's time varying, so we want to put 4t there because our u bar is 4ay. And then we're going to do it with respect to x, which is just the height of 1 meter, so 0 to 1. So when we do 2y with respect to y, we get 2y squared. We take the integration over 2 from 0 to 4t, and that just reduces to y squared from 0 to 4t. And when we plug in a 4t where y is, we get 4t squared So this will just be 16 t squared per meter. So now Faraday's law of EMF, the negative derivative of the flux with respect to time. Again, we take the derivative of the 16t squared, so it'll still be a negative. That just becomes 32 TB. That's our answer for that one.